Hello everyone, thank you for joining. I'm very excited to be part of DockerCon this year. Let me start with a quick introduction. My name is Ashish Sharma. I work for SS&C Eze as Director of Software Engineering. SS&C Eze is a Boston-based fintech company. We provide products and services in the stock market domain to automate and streamline the entire investment lifecycle. Quick stats about the company. We are in the business for over 25 years, serving 1,900 asset managers worldwide. As a company, we invest heavily into R&D. We have 1,050 plus employees with offices located across the globe. Before jumping on the main topic, I quickly want to talk about some of the core offerings to give everyone more context as to what we do. As Eclipse is our online investment management platform. A typical buy-side investment management firm, like a hedge fund or a mutual fund, they are constantly running through this investment management life cycle, represented by the circle, using the capabilities of our platform. And due to the nature of this business, we place a very high emphasis on high resiliency, high throughput, and low latency. There are a lot of different parts in the investment lifecycle. I will briefly touch upon the very core ones, starting with trading. This is where the active stock market trading happens. And this is a very interesting engineering problem for two reasons. First, the stock market in general is a vast and complex domain. And second, its execution has to be very performant. Our user can decide, okay, today I want to buy, let's say, 100,000 shares of Google. And he can enter this information in our application. We take that order, we route it to the brokers, and then in real time, we show you the progress on your order. It needs to be reliable. It needs to be performant. Even a sub-second delay in routing out orders to the market can cause a lot of money to our clients. Analytics. This is real-time analytics, like a real-time view of your profit and loss. Our users wants to know how much money they are making or losing as the market is progressing. So to put it in the context, think about this. The price on the security can change multiple times in a second. Multiply that with all the securities in the market, and very soon this becomes kind of a very big data set to deal with. Very interesting problem to solve. Compliance. We provide real-time compliance. You can create rules like no matter what, my exposure in technology sector should not go below 20%. So we'll run these compliance rules for you to make sure you're kind of compliant with your investment strategies. Modeling. This is useful for idea generation. You can run large financial models, or you can create hypothetical scenarios like hypothetically, let's say I want to invest $5 million in pharmaceutical sector. So how this decision would shape my overall portfolio. So some very interesting models and scenarios you can run. Operations, start of day, end of day operations. We interact with hundreds of different third parties on a daily basis. And each of these third parties have a variety of different formats in which they like to send and receive data. The fun part about this problem space is to build like sophisticated ETL and data pipeline to handle all these variations and make it seamless. Accounting. This is a bookkeeping of all the decisions you have ever made, and in a time series fashion. Coming on the main topic, in this talk, I want to share some elements of the journey we took from monolithic to microservice architecture and how Docker played a critical role into making this journey a success. Microservices and Docker is a powerful combination. I will share with you how it impacted our tech stack, developer experience, testing strategies, and delivery. And as I present this to you from my home office, there's no question that we are living in this unprecedented times. The spread of COVID-19 has affected the world in so many different ways, and one of these has been the stock market. During the very early days of pandemic, trading volumes among our clients was higher than we have ever recorded as a company. There's no doubt in my mind that had we not undertaken this journey, the Eclipse platform would not have been able to seamlessly scale to meet this unprecedented load. Okay, so let's see how adoption of microservices and Docker has shaped our tech stack. Our journey started with a simple idea. We wanted to build an online cloud-native investment platform. And when you're in this very early phase of the adoption curve, the one on the right, all you have is an idea, and you're working to see if this idea has any kind of potential market. So at that point, it makes sense to keep your tech stack simple. The very first version of the tech stack looks something like this. Our front end is a single page application written in Angular. We had around 10 to 12 backend services, all written in C#, deployed as Windows services. These services communicated to each other over RabbitMQ, and we used Microsoft SQL Server for backend storage. So overall, we kept it very simple, and this served us well for a short time. But as we added more and more features, it became a monolithic system over time. It got to a point where we were experiencing difficulty scaling it up. It required coordination across the teams during deployments. It impacted our time to recovery when things went wrong. There was no proper fault isolation. So in a way, we experienced our own share of traditional issues that we see with the monolithic architecture. And we knew we had to do something about it. At the time, microservice architecture was gaining attention in the development community, and it had a lot of promises. Around the same time, some folks from the organization also attended DockerCon, and they got excited about using Docker after they come back. So we applied both, and today the tech stack looks something like this. We have built polyglot stacks with loosely coupled services written in different languages. Preferred languages are Node.js, Golang, Python, and .NET Core. But we encourage our teams to explore and experiment with different tech stacks to solve different problems. Reason being, for example, if you're building an ETL pipeline and using a language which doesn't have a rich ecosystem for data manipulation, you would be burning a lot of development cycles trying to fit it in. Docker is a big part of our ecosystem. All services and infrastructure components, they run as Docker containers. We have 140 plus distinct services running in prod, with more coming up every week, every month. The messaging infrastructure is now powered by RabbitMQ, Nginx, Consul, and Amazon Kinesis. We have extended our backend storage to include MySQL, and we heavily rely on Redis for caching. This is the current state of tech stack, and it's continuously evolving. So wait, now I have to worry about microservices and polyglot stack both? Adoption of microservices architecture alone is a steep learning curve for everyone. No question about that, right? You have to worry about decomposition patterns, data sharding, API boundaries, service-to-service communication. There are a lot of different things that you have to worry about. Polyglot stacks comes with their own set of problems. There are too many options to choose from in terms of languages and frameworks. How do you even manage an infrastructure with so many heterogeneous elements without going insane? A word of caution about polyglot stacks. Maintaining a true polyglot stack is difficult and it requires a strict discipline. Our own internal development culture and discipline has evolved over time to put us in a spot where we can better manage against potential pitfalls, but it requires very strict discipline. I will talk about how we manage Eclipse infrastructure with polyglot stacks. Uniform packaging. All our services are packaged as Docker containers. Heterogeneous services in a uniform package makes it much easier to operate and reason about the system. It's a huge relief to our infrastructure team. Uniform packaging. With uniform packaging, it makes environment definition files simple. So then it's much easier to create consistent environments. You can reliably spin up like a staging, test, performance, and those environments look exactly identical to your prod environments on a click of a button. Dynamic scaling. Once you have environment which is simple and consistent, it further makes it easy to dynamically scale it up and down. Currently in Eclipse, we support scaling based on resource consumption. So say if your CPU goes above certain threshold, we auto scale, or based on time by looking at the service usage patterns. And this has been very useful in the recent times. With the COVID-19 impact on the stock market, our system was able to dynamically scale up just fine. It also simplified our CI/CD toolchain. In the monolithic days, in the absence of Docker, we had like 10 different tools for building, packaging, deployments. Now it's all simplified with just using Jenkins as a Docker CLI. Another element that helps to manage the complexity is consistent adherence to standards. Standards are important. It helps you keep checks and boundaries in place for teams to operate in a unified and safe way. And it's easy to do in monolithic architecture and monostack, right? You just have one language to worry about, and all the components coexist together, so you don't have to worry too much about like API boundaries and things like that. How do you make standards in polyglot stack? We maintain our own set of internal standards, which are agnostic to any framework or language, and they are held and enforced at a higher level. Here are a few categories. Resource access. These are the things that happens within your service, like accessing a database or a cache, authentication, authorization. How do you make sure teams are using consistent patterns across the board? So to solve this, we have written service templates in all 4 languages, and they come with these predefined patterns to address all these category of concerns. So for example, if there are let's say 30 services in Node.js, they all will be using the same template, and they remain consistent like that. API boundaries. Since there is no binary sharing in microservices, services are talking to each other over, say, REST or GraphQL. This becomes very important. Your API needs to look and feel consistent for both internal and external consumers. We solve this by creating a set of API standards, internal API standards, that all services have to follow. We use Swagger as an API documentation tool to give that nice look and feel. And we also embrace contract-driven development, and this is a must-have discipline. A workflow can span multiple services owned by different teams, and those different teams may use different languages. So that makes contract-driven development a must-have practice. Bootstrapping, how your services get configurations and secrets when it starts. Well, we solve this problem by extracting this responsibility completely out of the service. So when a service starts, it can expect all the configurations and secrets to be available to it in terms of environment variables. And Docker made this part very simple. So all these measures come together to ensure consistency between polyglot services and allow developers to kind of focus more on the business logic. Let's take a look at how adoption of microservices architecture and Docker has enabled better developer experience. And to understand this better, I will start with how the developer experience used to be back in the monolithic days. Then I will show you how the developer experience looks today and how this has been the life-changing for us. So in monolithic days, let's say I want to work on a story. So my developer experience would be something like this. Come to office, drink my coffee, the most important thing for me in the morning, download the code from the repo, build it, I will probably drink another coffee, then restore database locally, register services, configuration, and this is a big step. So I might end up drinking 3 more coffees when I'm doing this. Then it would be lunchtime, and hopefully after lunch, maybe I can work on a story. I personally have spent hours and hours setting up my development environment, and I took it even further. I would not even download the latest code. I would work off the old version of the code for as long as I absolutely don't have to. And working with the non-latest code actually came with its own set of problems. It resulted in more issues when they finally committed to the mainline. Today, it's very different. Like I said earlier, we have 140 plus microservices, and we didn't want developers to run all 140 services locally on their system. So this forced us to kind of rethink developer experience, and we came up with a hybrid approach. Now a developer only runs the service he wants to work on locally on his laptop, and everything else, the UI, the backend services, the infrastructure components, they all come from a shared development environment. So the developer experience today looks something like this. I come to office, start drinking my coffee, download the code that I want to work on, then I run Docker Compose up, and that's it. I have a working system. And at that point, I'm probably still drinking my first coffee. And this is huge. I have a working local environment in just a few minutes. Earlier, I would refuse to download the latest code, but today the first thing I do is to get the latest code, and getting a simple local environment is only takes a few minutes. No more working with the old version of the code. So let's take a look of how this hybrid service development approach works in practice. In this demo, I will show you how we set up the local service instance and use console to register my service to a shared development environment. Okay, so this is one of the microservices. It's written in Node.js. This service handles the life cycle of a stock that our users can borrow for short trading. It's one of the trading strategies. Here's a Docker Compose. This is the local console server I was talking about, and here's the service that I want to work on locally. I want to spin this up locally, and this is the database that comes with the service. Okay, so here I have Docker for desktop dashboard. There are no containers running at this time. So now let's go ahead and run Docker Compose up. So as you can see on the right, it started my stack with all three containers: the console, the local service, and the database. So now what I can do is I can go to my web page, which is hosted in a shared development environment. I need to log in as myself. So this is, again, this UI is coming from a shared environment. And I need to go to trading and locate. Okay, so now what I'm trying to do is I'm going to make some UI edits that should generate a request. And my hope is that this request should reach to my service running locally on my laptop. And we'll see that in the logs. Okay, so let's see here. I'm seeing some logs here already. Let me search here for Google. Okay, so here. Okay, here, perfect. Here's a request that I made from the UI. Great. So I have a local working system in just a few minutes now. And this makes it very easy and straightforward to develop a service in isolation. And also at the same time, working with the full and latest context of the entire running application. This has been life-changing. We also migrated from mono repo, which is like a one gigantic single repo with all the code, to micro repos, where each repo represents a standalone service or a UI component. So when a developer wants to work on a service, he's only downloading the code for that service and nothing else. Docker further makes it very easy to kind of write self-contained code, meaning the code comes with its own explicit set of dependencies, and it knows how to go and get them. It comes with its own SDK to build and run tests. It knows how to package itself in terms of deployment unit, which is a container, and we get all these nice benefits without really relying on any of the system-wide packages. All you need really is Docker for desktop and any laptop. And it's immutable package, so it's not going to change between your dev and test and UAT and prod. Like, gone are the days when we used to find issues because of a mismatch in the dependencies between your local and any other environment. It further makes onboarding simple. So when your code is small, it has a well-defined responsibility, it is self-contained, and spinning up a local dev environment only takes few minutes. It makes onboarding a new developer much easier. Another great benefit we see is a massive trend of cross-team PRs. So let's say my service consumes an API, and this API is owned by a different team. And if I need like few more fields from this API, so what I would do is I will download their repo, and I will see what patterns they are using, and I will quickly create a PR myself. All they have to do is just review it. Here's a chart based on our internal data. This is a weekly pull request graph. Team A here is making somewhere between, say, 15 to 20 PRs in a week. And then there's this sudden drop here. It actually turned out that Team A was busy making PRs into Team B's repo. So we see a lot of patterns like this. Okay, so how adoption of microservices and Docker has impacted our testing strategies. After we decided to move towards microservice architecture for our mainstream development practice, we knew testing was going to be challenging. As we added more and more services, we observed an interesting trend. The teams were relying more and more on the integration tests to test their services, which was not great. Too many integration tests can slow down your delivery pipeline, and they can be very flaky, meaning they may fail for very non-obvious reasons. So we had to shift left and think about how we want to test our services. We enabled our teams to develop services in isolation, as you saw in the previous demo, and we wanted to do the same for testing. How can we test our services in isolation with more confidence? So using some of the microservice architecture principles in Docker enabled us to do exactly the same. I will show you how. The diagram on the left, you can think of it as a service. This service exposes multiple resources as an API, like resource 1 to n here, and its implementation is deep layer of stacks all the way to the database. The small boxes here represents unit test. We take a small unit of code and we test it thoroughly. But unit test alone doesn't give us enough confidence that when all these units coming together, they are going to work as expected. And that's why we need service tests to test the depth of the service. The long ping boxes here can be seen as service tests, meaning if I call the resource 1 API from outside, it will exercise all the layers including the database, and produce an expected result. We all love unit tests, right? They're fast, they're easy, they're consistent, they clean up after each run, and they produce this nice code coverage reports, which gives us a lot of confidence about our code. Wouldn't it be nice if service tests were as reliable as and as easy as unit tests? So what are the challenges with service tests? Set up dependent services and test data. Do I need to run do I need to run all the services that my service depends on? Maybe those services depend on more services, so it makes a deep graph of services. And do I need to run all the databases that these services use? So building this environment with deep graph of services, it's expensive, right? And it's unstable. It's going to be flaky. And even if I manage to do all this, I know it will be very slow to execute, and I practically cannot trigger them on every check-in. So let's see how microservice architecture and Docker helps us with these points. Starting with dependent services. When you're operating in a microservice architecture, as a service, you really care about two things: your immediate consumers and your immediate dependencies, and nothing else. No layers beyond that, just your immediate dependencies. Using this to our advantage, we created a simple mocking framework that was inspired by the web crawler technique. So as a service, I know all the APIs I depend on upfront. Like I know all the APIs I'm going to call when I execute any workflow. So now what I can do is I can actually tell this mocking framework about all these APIs, and this mocking framework can then further can go to these APIs as like a crawler and download the data from those APIs and save them in a JSON snapshot. And later during the test run, these snapshots can be served as mock. So my service cannot really tell the difference if the data is coming from a real service or if it's coming from a mock service. So this solves our problem of deep graph of services. The next step is to build a reliable test suite. Our service test suite looks something like this. There are 4 containers: the service container in the middle, the one we want to test, the database container that comes to the service. It has a mock container, which is going to serve the JSON files, the files that we downloaded with using the crawler. And it has the test client container, which is going to execute test against the service by invoking API calls. Okay, so let's see how this works in action. In this demo, I will show you the crawler-based mocking technique to download the snapshot of the immediate dependencies, and then I will run a set of service tests. Okay, so here's the same service again. I need to find crawler, so in the test PDDs crawler. Okay, so I want to show you API mappings. Okay, so here they are. So these are the APIs that my service depends on. I know them upfront, so I can add them here. What this framework will do is it will go over these APIs and download the data in JSON files. Okay, so let me run the download tool now. So what it is doing behind the scenes, it's going to one of the shared environments and it's looping over all those APIs. It's going to download these files that I will show you after it's done. Okay, so let's see here. Okay, here's the whole list of files that it downloaded, right? The activity of downloading the snapshot is kind of independent of running the tests. The frequency of download really depends on the stability of the dependent API. Like if it is a brand new integration, then you might want to take frequent snapshots. Otherwise, you can take it like maybe once a month. Okay, so now let's spin up the test suite. Okay, so what it will do is it will create the 3 containers. One, the service itself, the mock container. This mock container will now serve the JSON files that we just downloaded, and it will serve it as mock, and the database container and the service container. Now let's run the test container, the BDD test container. Okay, so now you can see on the right that it started a test client container. This client container is making request to the service, HTTP request to the service. The service is then talking to the mock in order to process those requests or the database, and then it's returning result back to the test container, the test client container, and test client container is further kind of validating the results on top of it. Okay, so it's done. Couple of things to notice here. Let me scroll up. Okay, it ran 108 tests in 20 seconds, super fast, right? And then it generates this nice code coverage report. So with little innovation, it is possible to get code coverage for all running services. And so what we have been able to do just now is to test the full depth of the service in isolation, right? And the characteristics of these tests are in line with the unit tests. They're easy to write. The adoption of this style of service test has been impressive. Almost all the teams are doing it now. They're fast since everything is local, and as we saw, it ran 108 tests in 20 seconds. So not as fast as unit tests, but relatively fast. They are consistent. That means they only break for real reasons and not because of some flakiness in the environment. Code coverage. With some innovation, it is possible to get code coverage from a running service, as you saw in the demo. The immutability aspect of Docker container makes cleanup super easy. Just restart the containers after you're done. And they trigger on every check-ins. Our Jenkins CI pipelines are set up in such a way that it executes these service tests upon every check-in. And the same service test suite can be further used for other style of test. Here is an example of how we run chaos test within the same setup. So this is a chaos scenario where we want to calculate the profit and loss based on the start of day price if the real-time API fails to return the data. This way, the way to do it is kind of by hijacking one of the standard HTTP standard headers and tag it with some unique value. In this case, price returns 500. When the service receives this request, it doesn't do anything with these headers. All it has to do is to make sure it should pass all these headers to the downstream calls, the mock in this case. Now the mock is a little bit more intelligent, and when it sees this special tag, it will return 500 status code instead of returning the real result. And that would make the service kind of fall back into this chaos mode. In this case, use the start of day price. So in this way, we are able to test the resiliency of the system in isolation. And this same setup can be used for other different types of tests. After the adoption of microservices and Docker ecosystem, it completely changed the way we deliver software. And to appreciate this, I will show how we used to deliver back in the monolithic days and compare it with how we deliver it today. So back in monolithic days, we had weekend-only deployments and a dedicated team to do it. It was a painful process. A dev from each team would be on call in case something goes wrong. It required extended downtime, and the rollbacks were very, very painful. And since it was like weekend-only deployment, there were a lot of changes that are going into it. So if there was a problem, we had to roll back all the changes. Today, we have daily, anytime deployments. We have empowered our development teams to push the code to production. They are deploying multiple times in a day, and all deployments are zero downtime. And the rollbacks are much easier now. Just only roll back the problematic service. Here is a quick stat on the deployment history. We deployed 554 times in last 60 days, with moving average of 10 to 12 deployments a day, and max reaching to 21, 22 deployments, those long peaks there. The gaps here you see are probably the weekends, so we are not deploying on weekends anymore. I will quickly touch upon patterns for safe delivery, and I choose these two, the dark launch and the feature toggle, for two reasons. First, if you are in the journey of migrating from monolithic to microservices, these two can be real good assets. And second, they don't require any sophisticated setup. You can just do it with simple setup. Dark launch is a practice where, imagine if you have a V1 code path and you want to migrate to V2. So the first thing is to clone the input that's going into V1, then execute both V1 and V2 code path in parallel, and execute the V2 with the clone input. And then you can compare the results of V2 against the V1 for correctness and performance. So this will allow you to gain more confidence in your new code. Just make sure V2 code doesn't mutate the state of the system, otherwise you'll have issues. Feature toggles. So once you have gained enough confidence about your V2 version of your code, you still need to be careful when rolling it out in the production. So you can limit the blast radius by using feature toggles. So in the workflow, create a switch based of toggle. And if the toggle is on, run the V2 code path, otherwise continue on V1. So in case something goes wrong, you can immediately turn off the toggle. It will improve your mean time to recovery significantly. I want to wrap this up with key takeaways, starting with tech stack. Microservices with polyglot stacks are truly magical. It can further amplify your ability to react to changing markets, but it requires strict engineering discipline. Developer experience. Invest into making your developer experience as quick and as smooth as possible. Your developers will love it. Testing in microservice world can be very hard. Shift left. Think about how to test your services in isolation. Delivery. Apply standard patterns for safe delivery. Your focus should be to improve your mean time to recovery. Once you have achieved this level of maturity in the microservice architecture, where you have polyglot stacks, services can be developed and tested in isolation, teams are empowered to push code to production, your software development lifecycle will absolutely run on steroids. Thank you.